Well, we were to consider what is called Cauchy's criteria for uniform convergence of a sequence of functions. So let us begin with that. Cauchy's criteria for uniform convergence. Okay, so as usual we will take a sequence of functions fn from E to R, and we shall say that this sequence of function satisfies this Cauchy's criteria. Okay, we say that, so this fn is said to satisfy Cauchy's criteria if for every epsilon bigger than 0 there exists n0 in n, such that for all n and m bigger than or equal to n0, okay, such that n and m bigger than or equal to n0, this implies mod fnx minus fmx is less than epsilon, and this should happen for every x in E. Okay. Suppose we had simply stopped here, it would have simply meant that this sequence of real numbers f and x, that is a Cauchy sequence. Okay. But what we want is something more. Okay. What should happen is that for every x in E, this mod f and x minus fmx should be, that means this n0 should be again independent of x. Okay, that is n0 which should work for every x, such that mod fnx minus fmx is less than epsilon. Okay, sometimes this sequence is also, such a sequence is also called uniformly Cauchy. Okay. Okay. We also say that fn is a uniformly Cauchy sequence. Okay. Now what does the criteria say? That if you are given a sequence of functions, then that converges uniformly if and only if it satisfies this Cauchy criterion. Okay. So that is the theorem. Okay. Let fn from E to R be a sequence of functions then fn converges uniformly if and only if fn satisfies Cauchy's criterion, or in other words, if and only if fn is uniformly Cauchy, fn satisfies Cauchy's criterion. Okay. Okay. Now before going to the proof of this, let me again say something which I said yesterday. Okay, that is we had defined yesterday this set B of E. Okay, this set of all bounded functions on E. Okay, and on that we had defined a norm and metric induced by the norm, and that metric we have called D infinity. Okay. Right. Okay. So what is, okay, let us recall what is D suffix infinity. That is D suffix infinity of f and g. This is nothing but, okay, norm of f minus g, that is, or which is same as supremum of mod fx minus gx for x in E. Okay, and that is a metric. Okay, and is it clear that saying that a sequence is uniformly Cauchy, or saying that the sequence satisfies Cauchy's criteria, it's same as saying that this sequence is a Cauchy sequence in this metric, right? Okay, because what this means is that suppose you take the supremum over x in E, then this says that D between fn and fm is less than epsilon. distance between Fn and Fm is less than epsilon in that metric. Okay. So of course you know that in any metric space, if a sequence converges, it is a Cauchy sequence, right? That is true in any metric space. Converse is true if it is a complete metric space, right? So this theorem essentially says that this is a complete metric space. Okay, right? Okay, now let us go to the proof. Okay, this part is relatively easy to prove. That is, if Fn converges to F, then it satisfies Cauchy criteria. Again, as I said, to show that if a sequence converges, it is a Cauchy sequence. That's a straightforward thing. But anyway, let us go through it. Okay, suppose Fn converges. Suppose Fn converges. Okay, converges to some F uniformly. Okay, then we have to show that it's a Cauchy sequence. To show that it's a Cauchy sequence, take some epsilon and show that such an n0 exists. Okay, so let epsilon be bigger than 0. Okay, alright. Then since we know that Fn converges to F uniformly, we can use that. Okay, there exists n0 in n such that for all n bigger than or equal to n0, we have mod of Fnx minus Fx less than, I can say less than epsilon by 2. Okay, and this should happen for every x in E, for every x in E. Okay, and this is a standard way of going. Now you take any n and m bigger than or equal to n0 and look at Fnx minus Fmx. Okay, so now consider mod of, okay, then mod of Fnx minus Fmx. What is to be done is clear. Okay, add and subtract Fx. Okay, add and subtract. So this is less than or equal to mod of Fnx minus Fx plus Fx minus Fmx. Okay, and each of this quantity is less than epsilon by 2. So this is less than epsilon by 2 plus epsilon by 2, and that is equal to epsilon. And again, since this n0 was independent of x, this works for every x in E. So whatever we have done about that n0 should work for every x in E. Okay, so this also is true for every x in E. Okay, so this shows that Fn satisfies Cauchy's criterion. Okay, that is what is meant by, what we want to show is that for every epsilon there exists n0 such that whenever n and m are bigger than or equal to n0, mod Fnx minus Fmx is less than epsilon for every x in E. Okay, so that's what we have shown. Okay, alright. Okay, now next is the other way. Okay, now we assume that Fn satisfies Cauchy's criterion. Okay, and from that we need to show that it's a uniformly convergent sequence. Okay, so suppose Fn satisfies Cauchy's criterion. Okay, now first of all what we can do is that take any x in E and consider this sequence Fnx. Okay, consider this sequence Fnx. Okay, then that is a Cauchy sequence. Okay, right, because for each x in E this is satisfied, so it is same as saying that this is a Cauchy sequence of real numbers. Okay, so then Fnx is a Cauchy sequence of real numbers. So of real numbers. Okay, and real line is complete. Okay, so once a sequence is Cauchy sequence of real numbers, it should converge to some real number. That real number we shall call fx, okay, right? So and hence converges to some real number, and we call that real number fx. Let's say fx. Okay, so this can be done for each x in E. This can be done for each x in E. So that means this defines a function from E to R. Okay, so that is this defines a function f from E to R, and what is the how the function is related to the sequence fn? Each fx is a limit of this fnx. Okay, each fx is a, so it is given by this f of x is equal to limit n tends to infinity fnx. But at this point we have only said that it is point-wise convergence. Okay, because how did we construct f? We started with some x and said that the corresponding sequence is a Cauchy sequence of real numbers, and hence that has a limit. That limit we have taken, and that limit we have called fx. So with this construction we have only got a function f which is a point-wise limit of this sequence fn. But that is not what we want. Okay, what we want is a limit should be uniform limit. Okay, so obviously if at all a uniform limit exists, that has to coincide with point-wise limit. It cannot be some different function. So we should try to show that this is a uniform limit. Okay, so that means, okay, but this is we can write this as a claim. Okay, what is the claim? We want to show that fn converges to f uniformly. Okay, fm converges to f uniformly. Okay, now let us take again some epsilon bigger than 0. Okay, then what we can say is that since we already know that fn is a uniformly Cauchy sequence, that is fn satisfies Cauchy criteria, using that there exists some n0. Okay, so there exists some n0 in n such that m and n bigger than or equal to n0. This implies mod of fnx minus fmx less than epsilon. Okay, and again this should happen for every x in E. That is, the same n0 should work for every x in E. Okay. Now the argument which is given after this is a fairly standard one. What we say after this is that this is true for every m and n bigger than or equal to n0. Okay, right. So what we do after this is keep n fixed, or one of them, either m. Let us say suppose keep n fixed and let m vary. Okay. Let m vary means consider all possible values of m bigger than or equal to n0. That means let m go to infinity. If m goes to infinity, what should happen? This should go to fx. This should go to fx. Okay, but this inequality is true for every m. That is, mod fnx minus fmx is less than epsilon is true for every m. So in the limit, at the most, what could happen is that this may become less than or equal to. Okay. Okay. So this is what. Okay. So we can say after this is keep n fixed. Keep n fixed and let m tends to infinity. Okay. Then since it is because of this, we know that if m tends to infinity, fmx goes to fx. Fmx goes to fx. So this will go to fx, and hence this will become then mod fnx minus fx. Okay, less than or equal to epsilon. But you can say this less than or equal to doesn't matter. Here itself we could have taken some number smaller than epsilon, and then we could have got less than epsilon. So that's a minor thing. Okay. Okay. So this means that fn converges to f uniformly, right? That is, given epsilon, we have found some n0 such that whenever n is bigger than that n0, mod fnx minus fx is less than epsilon. Of course, this again happens for every x in E. Okay. Is that clear? Okay. Okay. So again, let me again comment that what this theorem actually means is that space BE which we have taken is a complete metric space. Okay, all right. Now translating this to the convergence of a series, we get one useful criteria for convergence of a series. It is called Weierstrass M-test. Weierstrass is a name, so Weierstrass M-test. This is a test which helps in deciding easily about certain kinds of series which are uniformly convergent or not. Okay. So again, what we do is let us first see what the test says. Okay, the test is as follows. Again, we take a sequence fn from E to R. Okay, and suppose we have some numbers mn, let us say, such that mod of fnx is less than or equal to mn for all x in E. Okay, so suppose in our language this is same as saying that norm of fn is less than or equal to mn. Okay, because mod of fnx less than or equal to mn for each x in E, this is essentially same as saying that if you look at this norm of fn suffix infinity, this is less than or equal to mn. Okay, okay. So in particular you can take this mn as this number itself. Okay, you can take mn as this number itself. Okay, okay, and this is something that you can do whatever this is the sequence given. Okay, once fn is bounded, we can always talk of this, we can always take this mn. Okay, but what is something more. Okay, and now mn is a sequence of real numbers. Mn is a sequence of real numbers. So suppose this happens, and if you look at the series sigma mn, n going from 1 to infinity, converges. Okay, right? Then the functional series sigma fn, that is series of functions, then sigma fn, n going from 1 to infinity, converges uniformly. Okay, that is what, again recall what is involved. There should exist some number mn. In fact, this will be always a non-negative real number, such that for every x in E, mod fnx is less than or equal to mn. Okay, and the series sigma mn should be convergent. Okay, that's a series of positive numbers. Okay, and that is fairly easy to check because there are several tests for checking the convergence of the series of positive numbers. So that can be checked very easily. Okay, and then if that happens, we can conclude from this Weierstrass M-test that sigma fn converges uniformly. Right. Okay. For example, suppose something like this, you take the series sigma ed going from 1 to infinity, let us say sin nx by n square. Okay, that's a series of functions. Okay, okay, and what is the obvious choice of mn here? 1 by n square, because each of this mod sin nx is less than or equal to 1, so each of this is less than or equal to 1 by n square, and sigma 1 by n square converges. That's a well known thing. Okay, sigma 1 by n square converges. So this series of functions converges uniformly. Okay, and this way you can check the convergence, uniform convergence of a series in a fairly easy manner. Okay, so that is the idea of Weierstrass test. These numbers mn you can calculate in most of the cases. Okay. Again, remember, we don't have to have mn to be exactly equal to this. Okay, right? It can be any number bigger than or equal to this. Okay, all that we need subsequently is that sigma mn should be convergent. Okay, okay. So let us look at the proof of this test. It depends basically on what we have proved just now, that a sequence converges if and only if it satisfies the Cauchy criterion. Okay, so alright, there are, as you know, anything that you want to talk about the series has to be talked in terms of its partial sums. Okay, so let us say, let us take Sn, is equal to f1 plus f2 plus fn. Okay. And similarly, let us look at the partial sum of this. Okay, let us look at the partial sum of this. Okay. Suppose I call that as Tn. These are numbers m1 plus m2 etc plus mn. Okay. Now to show that this series converges uniformly, it's same as saying that this sequence Sn converges uniformly, right? That is what we want to show, right? Okay, so this is what we want to show Sn converges uniformly. Okay. Now by using the last theorem, we have seen that to show that a sequence converges uniformly, it is sufficient to show that it satisfies Cauchy's criterion. Okay, so that is what we shall show. Okay, we shall show that it satisfies Cauchy's criterion. Okay, all right. Now to look at the Cauchy's criteria, we will have to look at Sn minus Sm, right? Okay, that is, we have to show that for every epsilon there exists n0 such that whenever n and m are bigger than or equal to n0, mod of Snx minus Smx is less than epsilon. So first of all, let us calculate what this Snx and Smx are. Okay, so Snx minus Smx, okay, this is same as, okay, Snx is, because Snx is same as f1 plus f2 plus fn, and Smx is same as f1 plus f2 plus fn. So let us say n bigger than m. Okay, suppose we take n bigger than m. Okay, then this will be same as fm plus 1 plus fm plus 2 etc up to fm plus n. Okay, so we can say that this is same as sigma, let us say j going from m plus 1 to n fjx. Okay. So let us take the absolute value, then this will be less than or equal to mod fjx. Okay, right. And what do you know about this mod fjx? That mod fjx is less than or equal to mj for every x in E. Okay, so I can say that this is less than or equal to sigma j going from m plus 1 to n mj for every x in E. Okay. Okay. And now what can you say about this number sigma j going from m plus 1 to mn? We know that sigma mn is convergent. Okay, sigma mn is convergent. That is same as saying that Tn is, in fact this is nothing but, okay, this number is nothing but Tn minus Tm, right? Okay. Okay, and since sigma mn is convergent is same as saying that Tn is convergent, right? Okay, but if Tn is convergent, it is Cauchy, it is a sequence of real numbers, right? So now the argument after this is standard. Okay, what you can say is that given any epsilon, you can always find n0 such that whenever n is bigger than or equal to, n and m are bigger than or equal to n0, Tn minus Tm is less than epsilon. Okay, and if mod Tn minus Tm is less than epsilon, it shows that mod Snx minus Smx is less than epsilon for every x in E, which is same as saying that this Sn satisfies Cauchy's criteria, okay, and hence converges uniformly. Okay, that's the proof. Okay. Okay, so far we have just discussed what is meant by uniform convergence of sequence or a series, and how to check in particular Cauchy's criteria and this Weierstrass M-test. By the way, this Weierstrass M-test is a very practical and useful test, and using this you can check the uniform convergence of the series of functions in several cases. Okay, alright. Now let us go back to our earlier problem. What we wanted to know was that if each fn has certain properties, then does it follow that the limit f also has the same properties, at least under the condition of uniform convergence. We have seen that under the pointwise convergence that is not true. So let us now check about uniform convergence. Now if you look at the properties like continuity, then see till now we have taken this set E to be any arbitrary set, okay, we did not bother about what that set E was. But to consider the properties like this, if we want to talk about the limit or continuity etc., then the whole thing has to happen inside some metric space, right. So now we will take the set E to be a subset of a metric space, okay. So let us say that, okay, let us say that XD is some metric space, and of course subsequently when we want to discuss the differentiability, integrability etc., then we will have to take it as a subset of a real line, in fact an interval, okay. But for the continuity still we can take any arbitrary set in a metric space, okay. So suppose E is a subset of X, okay, and Fn is from E to R, Fn, and F is also from E to R, okay, and suppose Fn converges to F uniformly. Okay. Then what we want to say is that if each Fn is continuous, then F is also continuous. Okay. But instead of proving that directly, since the definition of continuity involves the limits, okay, we shall prove something about the limits, okay, and then whatever we want to say about the continuity will follow as a corollary, okay. So let us say that suppose this Fn has a limit as some point x. Now to talk about the limit, suppose I take this point x and I want to talk about the limit as Fn tends to let us say as t tends to x, okay. Then for that this x does not have to belong to E, right. You know that for talking about a limit, the point at which you are talking about the limit does not have to be in the domain, okay. But what it must be is that it must be at least a limit point, because in every neighborhood the function should be defined, okay, though it need not be defined at the point x etc. Okay. So let us say that suppose Fn tends to F uniformly and x is a limit point of T. Okay, and x is a limit point of E, and let limit, suppose for each Fn, limit of Fn t as t tends to x exists, okay. Suppose for each Fn, limit of Fn t as t tends to x exists, and suppose we call that limit as Ln, L suffix n, okay. Then what we want to say is the following, that this sequence Ln converges, and suppose L is that limit, then limit of Ft as t tends to x also exists, and that limit is same as the limit of this Ln, okay. Okay, so then limit Ln as n tends to infinity exists, that is, this is a convergent sequence. Also limit of Ft as t tends to x exists, and both the limits are the same, okay, and limit of Ln as n tends to infinity is same as limit of Ft as t tends to x, okay. That is limit of Ln as n tends to infinity, that is, this is n, okay, as n tends to infinity is same as limit of Ft as t tends to x, okay. Suppose we write this again Ln and Ft in their full form, because Ln is nothing but limit as t tends to x of Fn t. So suppose I write that here, that is limit, the left hand side is same as this, limit as n tends to infinity of Ln is limit as t tends to x of Fn t, okay, and this is equal to limit as t tends to x, and Ft is nothing but limit of Fn t as n tends to infinity, okay, because that is what we have assumed, that Fn converges to F, okay. So Ft is nothing but limit as n tends to infinity of Fn t, okay. So if you look at this last equation, you will understand what I said right at the beginning while discussing about uniform convergence. What we are saying is that if Fn converges to F uniformly, these limits can be interchanged, okay. Here you are taking limit as t goes to x first and then limit as n tends to infinity, whereas it is here it is the other way. Here you are taking limit as n tends to infinity first and then taking the limit as t goes to x of the same quantity Fn t, okay. Now let us prove these things one by one. First thing to prove is that Ln converges, that is limit as n goes to infinity Ln exists. But Ln is a sequence of real numbers, right? Ln is a sequence of real numbers. So to show that it converges, it is sufficient to show that it is Cauchy, okay, alright. And that we can show by using that since Fn converges to F uniformly, okay, it's also a uniformly Cauchy sequence. So let us start with that, okay. So let us say that let epsilon be bigger than 0, then there exists n0 in n such that n and m bigger than or equal to n0. This implies mod Fn t minus Fmt, this is less than epsilon, this is less than epsilon for every t in E, right, for every t in E, okay. Now since this is true for every t in E, we can let t goes to x, okay. This inequality is satisfied for every t, okay. So it will be, and we know that limit of this as t goes to x exists, that is Ln, limit of this as t goes to x exists, and that is Lm. So Ln minus Lm, okay, may not be strictly less than but less than or equal to epsilon, okay. In the limit at the most the inequality need not remain strict, but it will remain less than or equal to, okay. So we can say that letting t tends to x, letting t tend to x, we have mod Ln minus Lm is less than or equal to epsilon, okay. Now that shows that this is a Cauchy sequence, that shows this is a Cauchy sequence. So this implies that Ln is a Cauchy sequence, Ln is a Cauchy sequence, and since it is a Cauchy sequence of real numbers, okay, it is a Cauchy sequence of real numbers, and hence it should converge to some real number, okay? And hence converges, to some say real number L belonging to R, okay, right, okay. So we have shown this first requirement, that limit of Ln exists, okay, and suppose now, and we have called it limit as L. Now what remains to show, that that number L is same as this limit of Ft as t tends to x, okay. Let us go to that now, okay? Okay, so to show L is equal to, or let me write it this way, limit of Ft as t tends to x is equal to L. By the way, it is a standard convention in analysis, you would have come across this, that is, this equation means that this limit exists and is equal to L, okay. It means both the things, okay, that this limit exists and the limit is equal to L, okay, that is the meaning of this symbol, okay. So once we show this, is it clear that once we show this, then everything is proved, okay, that is once we show this, this equation is proved, this conclusion is proved, and this is nothing but say rewritten, we have rewritten the same thing in a different manner, okay. So this is nothing new, okay. Now the proof of this is again follows a very standard technique used quite frequently in analysis, sometimes known as 3 epsilon proof or epsilon by 3 proofs, etc. Okay. Basic idea is you just add and subtract some terms. Okay. See, what is the idea? We want to show that the limit of L, limit of ft as t tends to x is equal to L. Okay. Now by definition, what does it mean? That given epsilon, you should be able to find some delta such that whenever distance between t and x is less than delta, distance between ft and L is less than epsilon, okay. Now that means what does it mean practically? We want to show that this difference ft minus L is small. This difference can be made arbitrarily small, that is what we want to show by taking t as close to x as you want to. Okay. Now we know nothing about the difference mod ft minus L, but we know the difference about several other things by whatever we have assumed, okay. So basically we add and subtract those terms. For example, we know that mod ft minus fnt can be made small, okay. For example, I can write this, okay. We know that mod ft minus fnt, this can be made small because fn converges to f uniformly. Then we also know that fnt minus ln, that can be made small because limit of fnt as t goes to x is ln. So if you go t to x, this can be made small, okay. And then finally, if you look at ln minus L, this also can be made small, okay. If ln is close to, if n is sufficiently large, the difference between ln and L is small, okay. So what we can say now is this: for any t, this much is true, that mod ft minus L is less than or equal to mod ft minus fnt plus mod fnt minus ln plus mod ln minus L, okay. So we want to choose delta in such a way that this becomes less than epsilon, right. So we shall make the arguments in such a way that each of this term becomes less than epsilon by 3, okay. Or if you make each of is less than epsilon, the whole thing will become less than 3 epsilon, that also does not matter, okay. So that is why such a thing is called a 3 epsilon proof or epsilon by 3 proof or whatever, okay. Basic idea here is that you add and subtract some terms, okay. Okay. Now let us look at one by one, okay. When will this be small? Mod ft minus fnt, this will be, okay, so we will begin with this, let epsilon bigger than 0 be given, okay. Okay. We want to make this whole sub less than epsilon, okay. So we will try to make this whole thing, this less than epsilon by 3, this less than epsilon by 3, and this is less than epsilon by 3. Now out of this, these two, this and this will become less than epsilon by 3 if n is sufficiently big. So that choice we will make first, okay. That choice we will make first, okay. Okay. Now we can say that there exists, okay, let me call to begin with, there exists n1 in n such that n bigger than or equal to n1 implies mod ft minus fnt is less than epsilon by 3, is less than epsilon by 3, but one more thing is important. This happens because fn tends to f uniformly, this happens for every t in E, okay. This happens for every t in E. Okay. Alright, okay. Then since ln converges to L, we also say that there exists n2 in n such that n bigger than or equal to n2 implies mod ln minus L is less than epsilon by 3, okay. Right. Okay. So now if you take some n which is bigger than or equal to both of these, okay, say maximum of n1 and n2, then for that n both these inequalities will be satisfied, okay. So consider some such n, okay. So consider some n bigger than or equal to maximum of n1 and n2. Then for that n, this is less than epsilon by 3 for every t in E, and this is also less than epsilon by 3. Okay, all right. What remains is this. What is to be done about this? Now we will now look at only for that particular n, this n which we have chosen, this n which we have chosen. For that n, look at fn t minus ln. Okay. Now fn t minus ln will become small if t is sufficiently close to x, because that is what we have assumed, that limit of fn t as t goes to x is ln. Okay. So now what we do is choose delta in such a way that whenever distance between t and x is less than delta, this difference is less than epsilon by 3. Okay. So we can say, now what we can say is that for this n, since limit of fn t as t goes to x is equal to ln, there exists delta bigger than 0 such that wherever the distance between t and x is less than delta, distance between t and x is less than delta, this implies mod fn t minus ln is less than epsilon by 3. Okay, all right. Okay. Now the proof is more or less over. So given epsilon, we have found a delta such that whenever distance between t and x is less than delta, okay, mod fn t minus ln is less than epsilon by 3. Okay, mod fn t minus ln is, what is this n, what is this, which n, or what is this fn? This n is some number which is bigger than this n1 and n2. This n1 and n2 we have already chosen. Okay. Now once this is the case, since for this n is bigger than or equal to n1 and n2, for that particular fn, mod ft minus fn t is less than epsilon by 3. This is less than epsilon by 3 and this is also less than epsilon by 3. So this whole thing is less than epsilon. Okay. So that means we have given epsilon, we have found a delta such that whenever distance between t and x is less than delta, mod ft minus l is less than epsilon. Okay. That is same as saying that is same as showing this. Okay. Okay. All right. So that proves this theorem completely. Again, what is the theorem? That if each of fn has a limit as t goes to x, then f also has a limit as t goes to x, and that limit is nothing but limit of these ln's. Okay. Now as a simple corollary, we can say that if each fn is continuous, okay, then f is also continuous. Okay. So we can say that as a corollary of this, under the same hypothesis, that what is the hypothesis? That suppose fn tends to f uniformly. Suppose fn tends to f uniformly, okay, then in fact this can be studied even at a point, but okay, let us say at a point. If f is continuous, if each fn is continuous, fn is continuous, either we can say at some point x in E or at all points x in E, it makes no difference in the proof. Okay. Let us say if each fn is continuous, to begin with let us talk of some point continuous at some x in E, but this time I am taking x inside it. There I had taken just the limit point. Okay, x in E, then f is continuous at x in E. Okay, right. And in particular, if this happens for all points, that means if fn is continuous at all points in E, f is also continuous at all points in E. Okay. So in particular, if do you use this notation C of E? You are familiar? Set of all continuous real valued functions on E, that is C of E, that is f from E to R, f is continuous. Okay. So instead of saying in words that each Fn is continuous at all points x in E, I will simply say if Fn belongs to E for all n, Fn belongs to E for all n, then F belongs to not Fn E, C of E. Fn belongs to C of E for all n, then F belongs to C of E. Okay. In fact, this says something about this space C of E, but I will come to that little later. Okay. First of all, let us prove this corollary. You can say that proving this corollary is nothing really different. Okay. That is, suppose let me again look at it. Instead of saying now here, instead of saying that x is a limit point of E, we are now taking x belongs to E. Okay. We are now taking x belongs to E. Okay. Now, what is the meaning of saying that Fn is continuous at x? It means that this limit of Fn t as t tends to x, that is nothing but Fn of x, right? Okay, then, so this ln, this will be changed to Fn of x. Okay, okay, right? And what is the conclusion? It means that okay, that the limit of Fn x exists, then limit of Ft as t tends to x exists. Okay, okay, and that limit, okay, that limit is nothing but okay. See, remember this ln is nothing but now ln is nothing but Fn of x. Limit n tends to infinity, that is limit as t tends to x of Ft, that is same as limit n tends to infinity Fn of x. Okay, but what is limit n tends to infinity Fn of x? That is same as fx, because we have assumed that Fn converges to f. Okay, so this is nothing but f of x. Okay. So that means limit as t tends to x of Ft is same as f of x, right, which is same as saying that f is continuous at x. Okay, right. So essentially all that we do is we apply this theorem at the point x. Okay, we apply this theorem at the point x and then get that if each Fn is continuous, f also must be continuous. Only idea use this, if Fn is continuous at x is same as saying that this ln is nothing but Fn of x. Okay, and you just use that here, you get that limit of Ft as t tends to x is fx, that shows that f is continuous at x. Okay. Further, if this happens for all points x in E, okay, then f also must be continuous at every x in E. Okay. That is the thing, saying nothing extra. Okay, that is, once we show that f is continuous at, if each Fn is continuous at some x in E, then f is also continuous at x in E. So if the first statement is true for every x in E, this also should be true for every x in E. That's all. Okay. Okay. Now coming back to this notation. Okay. Okay. Let me again go back to this metric space, set of all functions which are bounded in E with respect to this matrix d suffix infinity. Okay. Right. We have shown that this is a complete metric space, right? That was the beginning. Okay. All right. Now in general, if you take any arbitrary set E in a metric space, and then every continuous function need not be bounded. Okay, but if you put an extra condition that E is a compact set, then you know that every continuous function is bounded. Okay, so now let us consider that. Okay, suppose E is compact. Suppose E is compact. Then this C of E is then saying that every continuous function is bounded, it's same as saying that C of E is a subset of B of E, right? Okay, then C of E is a subset of B of E. Okay, do you agree? Okay, in fact this is nothing but saying that every continuous function on compact set is bounded, right? This is nothing but saying in the words. Okay, since E is compact, every continuous real valued function is bounded. Okay, all right. Now what does this theorem say about C of E? Look at this last statement. If each, we have already seen that uniform convergence is nothing but convergence in this metric, okay, uniform convergence is nothing but a convergence in this metric. So what does this theorem say? That suppose you take a sequence Fn in Ce, okay, and if Fn, then obviously each of this Fn must be in Pe, and if Fn converges to F in this metric, then that F also belongs to C of E. What does that mean? That this C of E is a closed subset, okay, that C of E is a closed subset of this metric space, okay, alright. But suppose you know that the metric space is complete, and if a subset is closed, then what can you say about that subset? That's also complete, okay. No, you cannot say it is compact, but it is complete, okay, you can always say it is complete. So a closed subset of a complete metric space is again complete, okay. So so what this theorem says, or what this corollary says, that C of E is a closed subspace or closed subset of B of E. In fact, we can also say closed subspace, because the C of E, if you regard this B of E as a vector space, C of E is also a subspace, because C of E is also a vector space, okay, it is a subspace and it is a closed subset, or if you want you can say subspace of B of E, and hence complete, okay, and hence complete. That means what we have shown is that it's complete, okay. That means if you look at this space, whenever E is compact, if you look at this space C of E with respect to this metric, this is a complete metric space, okay, this is a complete metric space. Okay, right, in particular spaces like C of AB with this metric, supremum metric given by the supremum, this is a complete metric space, okay, alright. Now sometimes we are also interested in knowing, see, we have seen an example that every uniformly convergent sequence is pointwise convergent, but the converse is false, okay, in general the converse is false. So sometimes we also want to know what additional conditions can be put on a pointwise convergent sequence so as to make it uniformly convergent, okay. There is one very well known theorem in that direction, that is called Dini's theorem, okay. What it says is that if the sequence is monotonically increasing or monotonically decreasing, and if it is pointwise convergent, then it is also uniformly convergent, okay, right. But this is something we shall prove in the next class.